Active low signals use more LUTs because they require inversion before they can directly drive the control port of a register. This is because the Virtex-5 FPGA only supports automatic inversion of clocks. This means that the only signal that can be locally inverted without a LUT is a clock. This inversion must be done by consuming a LUT input. If you use hierarchical design techniques, such as partitions, keeping hierarchy, using cores, using multiple netlists, and using bottom-up synthesis, active low control signals can increase the use of control signals, again because the flip-flops do not have a programmable inverter. With hierarchical design, each signal would have a different name, and you would still have to run each signal through an inverter, which means that you are burning a LUT for each active low control signal in each hierarchical block. Hierarchical design necessitates this because the designer wants to keep and maintain hierarchy and partition their design to follow an incremental design flow. As you'll see on the next slide, this increases the LUT usage and wastes LUT efficiency. By using extra LUTs and running resources, we also can create timing problems and consume more power. So, bottom line, use active high control signals for sets, resets, and clock enables. In this example, we are distributing an active low clock enable, which has to be inverted at each flip-flop to drive the clock enable port. This would normally be absorbed into a LUT, but since it is a high fan-out control signal, it would be best to drive the clock enable port directly to save LUT inputs. But the problem is that the Virtex-5 flip-flop must receive an active high control signal to the clock enable port, so in this case it has to be inverted. This requires each component to waste an inverter. Likewise, since this clock enable is used by several other components that maintain their hierarchy, which is actually a good design practice, the LUT is wasted 5 times. Remember that the synthesis tools and the implementation tools cannot merge this logic into the same slice because the designer is not allowing the optimization across the hierarchical boundaries. Now this might not sound too bad, and it isn't, but if a designer has lots of hierarchical boundaries, he could waste a chunk of LUTs, and that is just not efficient design. So keep in mind this also means that sets, resets, and clock enables should all be active high in Virtex-5. It is important to remember that using dedicated hardware resources is going to free up extra slice resources, which will give the implementation tools the ability for your design to reach a higher speed. And for your information, Virtex-5 50 has approximately 12,000 DSP registers, and the Virtex-5 330 has approximately 48,000 registers. The DSP slice resources can be used for extensive math and DSP functions, so it is very important to remember that one of the biggest reasons to use a synchronous reset is that certain dedicated hardware resources simply don't have and don't support an asynchronous reset. While most arithmetic functions cannot infer the DSP resources, it still will require a synchronous reset to be coded if the user is going to infer a multiplier. Unfortunately, synthesis tools are just not capable of inferring many DSP slices into your design. You also should remember that using the dedicated hardware will allow you to get greater speed and higher device utilization. So, take the time to instantiate the DSP slices directly into your design, or better, use the core generator to build some of the most useful arithmetic functions that take advantage of these resources. As an FYI, consult User Guide 193, Virtex-5 Extreme DSP Design Considerations, for a more detailed description of what can be accomplished with the DSP slice. Many customers try to infer the block RAM resources and are disappointed when their synthesis tools don't give them the results they want, or don't allow inference of the memory component they want. Well, this is a typical limitation of most synthesis tools. One of the features of the block RAM resources is a dedicated output register that provides a synchronous read without using a slice. This is very commonly used, but what designers don't always realize is that, like the DSP slice, sometimes users try to infer an asynchronous reset and this prevents the synthesis tool from inferring the block RAM. This is because there is simply no asynchronous reset functionality built into the block memory. So to infer the block RAM's output register functionality, make sure you infer a synchronous reset, not an asynchronous reset. Just as I mentioned before, using more of the dedicated hardware resources will improve your device utilization and the speed of your design. So try to challenge yourself to use as much of the block RAM as possible for things like ROMs, complex combinatorial logic, finite state machines, or deep shift registers. This will free up hundreds of flip-flops and improve your device utilization. Make sure you are inferring the block RAM correctly by referring to your synthesis vendor's documentation. Usually, inferring block RAM requires a particular coding style and an attribute. If this does not work easily for you, keep in mind that the easiest way to get the block RAM is to build it with a core generator and then instantiate it into your design. But whether you infer or instantiate the block RAM, make sure you use a synchronous reset. Another big reason to use synchronous resets is that the synthesis and place and route tools are moving towards selectively demoding a synchronous reset from the control port to a LUT input. That means that in the case where we have a register with a low fan-out reset signal attached to it, the synthesis tool or the designer can selectively migrate the reset to a LUT input. This is advantageous because less timing critical and low fan-out resets can save the reset port for other functionality, like an asynchronous global reset. This would also allow the mapper to group unrelated logic into the same slice and improve device utilization and speed. Recall that a clock enable that is routed to a LUT input is no longer part of the control set, so the register is more likely to be merged with other flip-flops that don't have the same local reset. So keep in mind that this could be the biggest reason to code for a synchronous reset. As mentioned earlier, the synthesis tools do have the ability to migrate a synchronous reset to a LUT input rather than connect it directly to the reset port of the register. However, currently, your results will vary because not all synthesis tools do this, and the mapper currently does not do this. So always keep in mind to try to use the synchronous reset. Another good reason to use synchronous resets is that they are automatically constrained when users employ basic global timing constraints. For most designers, this makes FPGA design easier. Synchronous resets simply do not need any special constraints in the design. They also do not require any special switches in the timing analyzer for timing analysis to be complete. Synchronous resets are automatically timed by the Xilinx timing analyzer. As you may or may not know, asynchronous resets are ignored by the implementation tools. So if you build with an asynchronous reset, you have to make a path-specific constraint to cover those paths. If you use asynchronous resets in your design, you may know that they can lead to disastrous functionality. Synchronous resets are more predictable and are less susceptible to accidentally missing timing. Synchronous resets are also not susceptible to race conditions. But the bottom line is that chances are that if you use synchronous resets, your design will work right out of the box. If the timing analyzer says you are meeting timing and your functional simulation is working, your design should work. With asynchronous resets, there is much less certainty because there are a lot of things that can go unnoticed.